Before we begin this particular section, this particular lesson, I would like to point out an observation that we had just finished up a unit where we learned how to take the derivative, which we know is the slope of a tangent line. Our next unit is entirely about what is that stuff good for? What do you actually use the derivative to do? Some of it will be analysis of graphs. Some of it will be some word problems, seeing how you can use analysis of graphs and this technique to draw conclusions and to do other techniques to figure stuff out. But our next set of work is entirely about how do you use the derivative, not necessarily how do you take the derivative. One of the very first uses that the derivative is used for is determining maximum and minimum values of a function. Our learning objectives are very straightforward. Use the derivative to locate local and absolute extrema. Use the derivative to locate critical numbers. Those are things that come right hand in hand with each other. You can see our vocabulary at the bottom, and we can progress from here. First things first, vocabulary is going to play a big part about this. When you look at this graph, do you see a point that is higher than absolutely everywhere else or lower than absolutely everywhere else? I'm seeing a lot of heads nodding yes, so where is that? This point at the bottom would be an example of an absolute minimum. Well, the point itself is not the minimum. But this is an example of an absolute minimum. It is lower than absolutely everywhere else. The term global also gets used here. It's a global minimum because it's basically lower than the entire world of our function. Two pieces that are you'll have to get used to noting with this. You have the absolute minimum occurs at the x value, but it is a global minimum, an absolute minimum of the y value. When we actually start looking at some of our problems, a piece that's going to make more sense, and I'll try to make it help as we look more into it, you'll notice this point would have an x value, and it would have a y value. We would say the absolute minimum occurs at the x value, but the absolute minimum is the y value. It's the number. The absolute minimum is not the point. It's the y coordinate of the point. It's very common that students will make that mistake when they talk about absolute minimum, local minimum, maximum, minimum. Any maximum or minimum are also called extrema. So whenever I say extrema, you'll know I'm talking about either one. It just depends on how the graph looks. Well, that part gives us absolute. We would also like to be able to discuss a local minimum or a local maximum. That would refer to basically like the peaks or the valleys. Do you see anywhere that is higher than everything else around it, at least for stuff that's close by? Well, this would be a location. Now, obviously, this is a point that's higher up than a lot of other places. But if we zoom in and look at only this neighborhood, this window around the point, it's a minimum in the window. Same thing here. This would be a maximum in that particular window if we zoom in. And these other ones are as well. Each of these places that are a maximum or a minimum in a nearby window, those are called local extrema, a local minimum or a local maximum. And our primary learning objective today is how are we going to find these things? Well, to start off with, here's the sine function. You'll note it takes on the maximum value, an absolute maximum at a height of 1, but because of the repeating nature of a sine function, it's going to get repeated over and over and over. So can you create an equation that will give you the maximum values? Scotty, your intuition that we will wind up using the derivative is correct. But beyond that, we're not saying right now with the derivative, we're just saying, when is it true? Well, you'll notice it reaches its maximum at pi over 2. And if we cycled through again, there's 2 pi plus another pi over 2. So we have 2 pi plus pi over 2. You go all the way around the circle again, plus another 2 pi, plus another 2 pi. Every time we iterate through 2 pi, we get back to the height of 1. And likewise, if we go to the left, pi over 2 subtract 2 pi gets us to negative 3 pi over 2. In general, what we're noting is we reach a maximum of 1 at the x values, pi over 2 plus k times 2 pi, where k is any integer. So we get our we get a maximum at x equals pi over 2 plus k times 2 pi. And we've got an equation for it. What about this one? F of x equals x squared. Well, I'm not even going to take the time to go and use the calculator for that. We'll just do a quick sketch. What is the absolute value? The absolute minimum of f. Well, we can see it bottoms off here. The absolute minimum is the y value, which was 0. Where does that occur? At x equals 0. So there we go. We have the absolute minimum is 0. It occurs at 0. Okay, what about this one? F of x equals x cubed minus 1. Well, we know the general x cubed function looks like that. So we'll just shift it down 1 unit. So here we have a quick sketch of our graph. Where is a local maximum? Okay, the question was asked, how do you determine what local is? Like, where do you pick the square? It's local if you could pick any square, any rectangle, anywhere. Zoom in as close as you want, and it should still have this issue where it's reaching a peak or a valley in that box. You zoom in more, you zoom in more, you zoom in more. It's the idea of you can limit in on it as closer and closer and closer, and it's still going to be the highest point no matter what. Now, on the actual graph with a graphing calculator, you zoom in too much, and the calculator can't physically see the difference. You have to rely on algebraic skills to know it's not going to work. Or even though the line looks flat on your calculator, it's because your calculator can't handle the numbers that are so small. It can't see the difference between them that small. Well, do you see a point anywhere where it reaches like a peak, where it's higher than everywhere else nearby? Well, at the top, you could consider considering the arrow, but remember the arrow says it keeps going on forever. But we'd like to be able to say, well, what about where the action is going on? But when we're looking at this, we can see it does kind of flatten off, but then it starts coming back up. Okay, if we tried a bigger square, we still have the same issue with it. So for this particular one, it does not have a local maximum. I lied to you. Just because the questions say, where is it? I didn't include, just because I asked where is it doesn't mean that there is one. I could have said, where is it, if any, but then a lot of people know the if any is a clue that there just might not be one because. Okay, so pause the video, plug this thing into your calculators. Now in class I noted that I actually had the function changed and it didn't get corrected when I had the video. I apologize. This is what we needed to have graphed. So looking at this now, determine the x values of the local extrema. First of all, where do you see local extrema? In this tiny little window there, we should see one. And up around here, we should see one. And down there, we should see one, which will actually be an absolute minimum as well. Well, if we're trying to locate the x values, please note I'm not going to go through all three of them in the video. You can pause the video after I show you how you can use the calculator for this. But on our calculators, we can go into Menu, Analyze Graph, and you notice how they have the minimum and maximum features? They can use this. Well, we're going to wind up doing this multiple times, so I'm just going to start over on the left and say pick a lower bound, pick an upper bound, and then you can see it gives me the minimum for that tiny little window that I picked, for that neighborhood. And so this is one that, at least rounded, we can get a minimum, a local minimum, at x equals negative 0.686. We know that is rounded, not exact. And the value of the local extrema, the local minimum, occurs, or not occurs, but is the y value for our point, negative 0.545. That's one of them. And we will do this for the other two. We'll note when you go through and use this same feature, we will get a local maximum at an x value, but we will get the local minimum, local minimum. The local maximum is the y value. So we'll come back over and I'll quick go Menu, Analyze Graph, Maximum, left bound, right bound. Cool beans, we've got 0, 0. And we can come back and do the third one. Analyze Graph, Maximum. I didn't want a maximum, so I got to hit Escape because I can see on the graph that it's a minimum. Analyze, minimum, left, right, and we've got that as well. By looking at the graph, we can even identify when our global maximum is, or a global minimum, if they even exist. I'm not going to take the time to write them down, but we would have the minimum, or the maximum occurs at 0. It is a maximum of 0. It is a minimum at 2.19. It is a minimum of negative 12.4. Got to pay attention to the prepositions because, of course, the preposition determines which variable you're looking for, where it's at or what it is. Coming back, this is the extreme value theorem. I will note you don't need to know the name of it, but you do need to know what it says. The extreme value theorem tells us if you have a continuous function on a closed interval, you'll remember that's the same type of thing as what we pretty much had for the intermediate value theorem. This is a common assumption that we will make with a lot of our theorems. It's continuous over a closed interval. Then we would know, Scotty, you made the observation right away, it's the derivative. We'll get this horizontal line, we'll get a maximum or a minimum whenever we get a horizontal tangent line, wherever the derivative is equal to 0. And that's what this piece is telling us. If you want to find out where you get a maximum or minimum, you can start by looking where the derivative equals 0. But there are assumptions there. These bottom two actually provide examples that say you must make sure you have a continuous function. You must make sure that it is on a closed interval, including the endpoints. Because when we look at this particular function, this is an open circle. Is there an absolute maximum here? No, because we don't actually have this yellow circle. It's an open circle. And so we never get there. We can always get closer and closer and closer to it, but there's never one that's actually bigger than all the others because the circle's not included. Well, this type of thing can happen when you've got a non-continuous function. If the derivative doesn't exist, we still have problems with saying an absolute maximum. The derivative wouldn't exist because it was not continuous. Likewise, we'd have the same issue here. Can you have an absolute maximum on this one? We've got a vertical asymptote saying it's going upward toward infinity, so we don't actually include the endpoint. Likewise, over at the 0, we have another open circle. So you can get smaller and smaller and smaller, but you do not actually reach a bottomed-off minimum value because the endpoints are not there. These two graphs are designed just to show you, you do need to make sure you have a continuous function. You do need to make sure it's over a closed interval. If you don't make sure those conditions are met, the idea of, oh, just figure out where the derivative equals 0 can go wrong. You've got to make sure it makes sense. So, noting what Scotty had done, taking advantage of what Scotty had said, how do we actually use calculus to get them instead of using the calculator, instead of just looking at a picture? It's in what your first intuition was. If we have a horizontal tangent line, so the slope is 0, so the derivative is 0, that's where they can occur. Please, please, please note, this theorem says the derivative must be 0 to get a local extrema. That does not guarantee that there is an extrema there, a local maximum or a local minimum. It's a necessary condition, not a guaranteeing condition. Specifically, consider this one. We were just looking at this function before. Granted, we had it slid downward, but we had this piece where we noted there is not a maximum or a minimum. But when we take our derivative, y prime, 3x squared, y prime equals 0 when x equals 0. Well, just because x equals 0 gives us a horizontal tangent line, that does not guarantee we will have a relative or a local maximum or minimum. Our tangent line is here. But when we zoom in, was there a local maximum or minimum? No. This is a necessary condition. We must get a horizontal tangent line, but it does not 100% guarantee it. There are other conditions that we could add later on. That'll be the first derivative test that will actually tell us this. Okay, what about here? Graph absolute value of x. Where does the derivative equal 0? It doesn't. We know on the entire left-hand side, the derivative is -1. On the entire right-hand side, the derivative is +1. But at the point x equals 0, the derivative does not exist because of our sharp corner. So where does it equal 0? It doesn't. But do we have an absolute minimum? Yes. Right there. We have an absolute minimum at x equals 0, even though the derivative does not exist there. Once again, that goes back to this part. We need it to be continuous. We need it to be differentiable. And so we get this other part. A critical number is anywhere that the derivative will equal to 0 or the derivative does not exist. Good examples of critical numbers right here. X equals 0 was a critical number because the derivative did not exist there. Same thing here. We had a horizontal tangent line, so the derivative was equal to 0. Those values are called critical numbers. We put the name critical on it because they're really, really important. The critical numbers are where your local maximum, your local minimum might be. Again, it's not a guarantee, but they might be there. If you start looking anywhere else, you're guaranteed you will not get in a local minimum or a local maximum unless one of these things are true. We need it to be the derivative is equal to 0, or the derivative does not equal, or the derivative does not exist. If we wind up with a derivative that's like -0.5 or +5, if we wind up getting a derivative that's not 0 and it exists, there's no way that this could possibly be a local maximum or a local minimum, because it's basically saying I've got this piece going on like that. How could you possibly get a local maximum or local minimum when the function is still going up or still going down? It couldn't. I want to stress this again. Finding the critical numbers are the places where you might be able to get a local maximum or a local minimum. They're the only places you need to look for. Because they're the only ones that we need to look for, it's important that we can actually find them. Let's locate the critical values for this function. Well, again, it's where the derivative equals 0 or where the derivative does not exist. Either way, we've got to calculate our derivatives. So let's get f prime of x. What do we need to do? Well, it's a product, so we will need to use the product rule. We would have the first function multiplied by the derivative of the second. That's -1. Plus the second function multiplied by the derivative of the first function. So what's the derivative of x to the 3/5? 3/5 x to the 3/5 minus 1, so -2/5. Okay, so when we rewrite this, that would be -x to the 3/5 plus 4 minus x times 3/5 over x to the -2/5. In order to find the critical values, we have to figure out where does this equal 0 or not exist. It's a lot easier if you have a fraction. So in order to get a common denominator, we need an x to the -2/5. I'm sorry, +2/5. This was a negative, so I brought it down to the denominator. +2/5. And so we'd have to have x to the +2/5 for the numerator as well. That will allow us to rewrite this then. Well, 2/5 times 3/5, or x to the 2/5 times x to the 3/5. Just add those exponents. We'd get x plus 3/5 times 4 would be 12/5. And 3/5 times -x is -3/5 x all over x to the 2/5, which we could then rewrite 12 over 5 minus 8 over 5 x over x to the 2/5. And because these are both a factor of 5, we could then bring that down to our denominator, x to the 2/5 over 12 minus 8x. So algebra has given this is our derivative. When is the derivative equal to 0? Well, the derivative will equal 0 when the numerator is 0. So f prime of x equals 0 when 12 minus 8x is 0. So solve that. That's 12 equals 8x. Divide by 8 and you get x equals 1.5. This is one of our critical numbers. This x value will give us a horizontal tangent line. But what about where the derivative does not exist? When does this piece not exist? How about dividing by 0? If our denominator equals 0, then the derivative does not exist. So we could check to say, when is this piece equal to 0? So divide by 5. When is x squared to the 1/5 power equal to 0? When x is equal to 0. We could take the 5th power of both sides, which would have given us x squared equals 0. Square root then is how I got that part. So the two things we noted. 1.5 gives us a derivative of 0. That makes it a critical number. 0 makes us have a derivative that does not exist, which makes it a critical number. Our two critical numbers, 1.5 or 0. And we're finished. In order to find the critical values, take the derivative and then see where does the derivative equal to 0. You also need to look and say take the derivative, but see where it does not exist. That's a lot of the domain stuff that we were doing right away at the beginning of the year. You'll note these pieces that I was looking at, these were based on finding the critical values, and the last couple of ones we were looking at were saying, where do we have a local maximum, a local minimum? What would you need to do to find an absolute maximum or an absolute minimum? Well, with this one, we could easily see that we have a global maximum, or I'm sorry, a global minimum there. Our global minimum occurs relatively easy to find, and using the calculator, we were able to get what those values are as well. One thing to keep in mind, though, what if I'm not looking at the entire function? What if we're saying, I want to look at only these x values? Do we have an absolute maximum in that interval? Do we have an absolute maximum or a minimum in that interval? A global maximum is for the entire function. A global minimum is for the entire function. A local maximum or a local minimum is for a tiny little window. But absolute extrema are the highest or lowest on the window also. Not the whole function, but only the area you're looking. And that's what this piece tells us here. If we want to find an absolute maximum or an absolute minimum, they are restricted to certain places. An absolute maximum or minimum will only occur at critical numbers or at the endpoints. But in order to figure it out, we'll usually need to plug them in and get the function values. So here, find the absolute maximum and the absolute minimum for this function. Please note, we're not saying global maximum or global minimum. Only on the interval from 0 to 3, closed interval, is what we care about. So first of all, you'll notice it's a polynomial. Polynomials are continuous everywhere, so they're definitely continuous on this closed interval. What this stuff tells us, our absolute extrema will only occur at the local extrema for our critical values, our critical numbers, or at the endpoints. So we have to start again by saying, what are the critical numbers? We'll have to take the derivative and see where does the derivative equal 0? Or where does the derivative not exist? So let's do that. What is f prime of x? 6x squared plus 18x minus 24. We need to now figure out where does that equal 0. Because it's a polynomial, we'll know it exists everywhere. Well, let's say factor out a 6. X squared plus 3x minus 4. How does that factor? We should recognize two numbers that will multiply to give us negative 4, add up to positive 1. Positive 4 and negative 1. So where does this thing equal 0? At x equals negative 4 and x equals 1. These two numbers are the critical numbers, the critical values. This last piece, what our textbook and our authors call the closed interval method. Again, the name's not important, but the topic is. You will only get absolute extrema at the critical numbers, which we just found, or possibly at the endpoints of the interval. Well, you'll notice how negative 4 is not in the interval we're concerned with. Since negative 4 is not in the interval from 0 to 3, we don't care about that at all. It's outside what we're interested in. The only places that we could possibly get an absolute maximum or an absolute minimum are at the endpoints 0, 3, or at our critical number. These are the only three places they could possibly exist. Well, that tells us where they might be at. Does it tell us if it's a maximum or a minimum? Does it tell us really anything? Well, we know that there are only three places to check. That's great, but we don't know which is the highest for a maximum, which is the lowest for a minimum. We will actually need to take these pieces and plug them back into our function. What is f of 0? What is f of 3? And what is f of 1? I want to move these things over. If we can figure out those three values, we can just look at it and say, hey, this one's the biggest. Hey, this one's the smallest. So how do you want to do them? We'll just do some substitution. You're absolutely right, sir. 0 is the easiest one. I'm not going to bother using calculator for that. 0 plus 0 minus 0 minus 40. That's negative 40. 1 is also pretty easy because, of course, 1 cubed, 1 squared, and all those will be just 1s. So we will take 2 plus 9, that's 11, minus 24, negative 13, minus 40, that's negative 53. And if you choose to use the calculators for that, fine, I really don't care. It's perfectly acceptable to do it that way. And in fact, to do the last one, that's what I would like to be able to do. Let's just use the given feature of our calculator. Noting on the calculator, here's our function. Control, given that x is equal to 3. There we go, we have 23. And if we wanted to, I know we don't need it for this problem, but this is a nice little technique, of course, because if we did need the critical value over a bigger interval, we could then say -4 and get that one as well. If we needed it, we of course don't, but it's nice to be able to know this calculator shortcut for us. So I forgot what it was. 23. What we just found are the y values for where the absolute maximum, absolute minimum could possibly be. Well, which is the maximum then? 23. We get an absolute maximum of 23 at the x value of 3. We get an absolute minimum of -53 at the x value of 1. And so there we are, we're done. We can identify the absolute maximum and minimum by finding the critical values and then checking to see what are the y values of the endpoints and critical values. And here's our last one for the day. Hubble Space Telescope was deployed on April 24th, 1990. A model for the velocity of the shuttle during the mission from liftoff at time equals 0 until the solid rocket boosters were jettisoned at a time of 126. Please note that this stuff right here is telling us we're looking from a time of 0 to a time of 126. It's telling us what the interval is. Using the model, estimate the absolute maximum and the absolute minimum of the acceleration. Okay, so since we're talking acceleration, we need to get the acceleration function. How do you get the acceleration function? That's our second derivative. So we'll come back and now say, here's our velocity function. Hang on. This is the velocity function already. So this would be the derivative of the position function. Therefore, the acceleration function, acceleration is the first derivative of velocity. So let's just calculate that derivative quick. 3 times 0.1302 would be 0.003906 t squared minus 0.18058 t plus 23.61. That's the acceleration function. Our absolute extrema would occur at the critical values of the acceleration function or the endpoints. Well, our critical values come from the derivative. Okay, so we need to get the derivative of our acceleration function. So 2 times 0.3906 would be 0.007812 t minus 0.18058. So where does this equal 0? To get our critical values, we have to ask, where does that equal 0? Well, that would be when t is equal to 0.18058 over 0.007812. So let's plug that into our calculator and get our critical value. Students are doing that one for me, and we got an approximate value of 23.1157. So where could the absolute extrema be? Possibly at 0, possibly at 126, possibly at 23. But we will just plug those things into the acceleration function and see what we get. Well, I don't want to crunch all the numbers, so I'm going to use the calculator with the given feature again. Plugging this into our calculator, we would get, the question was asked, why aren't we using the original function? Because we want to know the absolute value or the absolute maximum of the acceleration function. And so everything has to be based on that. This one, they could have given us the acceleration function right off the bat, but they chose not to do it just to make sure that you still remember the connection between velocity and acceleration, and that it's not just, oh, I see absolute maximum, so I'm going to take a derivative and then just do the stuff. Basically, the problem was phrased this way to make sure that we actually do understand the connections between things and aren't just memorizing a process. Certainly knowing the process is important, but if you don't know what you're supposed to be doing the process on, it doesn't help. And so coming back, we had x squared. All right, we have our function plugged in. Given that, oh, wrong one. Yep. Given that x is equal to 0, we would get an acceleration of 23.61. Given the other endpoint of 126, we get an acceleration of 62.86. And our last one, given that we had our critical value, which was 23.1157, we get that. So over the interval, where do we have the absolute maximum? Well, the maximum acceleration was here. We have a maximum acceleration of 62.8686, which occurred at the x value of 123, or the t value, the time. Where did we have an absolute minimum? The absolute minimum was 21.5229, which occurred at the x value, the t value for time of 23.1157. Noting that process then finishes us off with our learning objectives. Whole point today, locate the absolute extrema, which would be at the critical numbers or the endpoints. Locate the local extrema, which would be only at critical numbers. So of course, since both of those rely on critical numbers, you need to be able to find the critical numbers.